Hello. I hope you're having a wonderful spring break. I just want to take a moment to talk more about composition of relations. So, this was back in section 6.1. And to review, let's just go over the definition of it. So, let R be a relation from a set A to a set B. And let's say we have another relation, S, that goes from set B into set C. If we want to know what the composition of R with S is, it is a set of pairs of the form AC in the Cartesian product of A with C, where AC is in our composition of functions if and only if there exists some element B in set B such that AB is an R and BC is an S. So we're kind of saying AC is in our composition if and only if we have some sort of element B that bridges between A and C, right? So let's do an example of one of these. And our first example, we're going to just look at some simple sets here. So let's say we have some set A. No, not set A. We'll have A equal the set containing elements A, B, C. And B will be the set containing 0, 1. And C will be the set containing A, B, and D. Okay. So you can see that A and B have, A and C have the elements A and B in common. Okay. Now let's consider two relations. Let's consider a relation R that is a relation from A to B, and R is going to have the elements A comma 0, A comma 1, B 1, and C 0. So again, this is relation R that relates A to B, set A to set B. And now let's come up with another relation. And this relation we'll call S, and it's going to relate elements in set B to elements in set C. So the elements in relation S are 0A, so 1 comma B, and 1 comma D. Okay. Now we're going to use our definition to find the composition RS. So when we are using this notation, little r, little s, this says relation R is first, then relation S. Okay. So if you've been in calculus or pre-calc or something where you've had that notation that reads right to left, this is different. This is left to right. So R, then S. Okay, and if you're not familiar with that other notation, then you don't need to worry about it. So we're just read left to right here. Okay, so one way we could help understand this problem is to draw just a picture. And so I'm going to make these three rectangles that represent our sets A, B, and C. And I'm going to list the elements in each of those sets vertically. So for capital A, it contains elements little a, little b, little c. For set capital B, it just contains 0 and 1. And for set capital C, that's going to contain A, B, D, right? So R is going to go from A to B. So we're going to first look at the element in R. Let's read left to right. So we'll take element A0. That tells us to draw an arrow from A to 0. And our next element R, A1. So we draw an arrow from A to 1. And then we look at the third element in R, B1. So we're going to draw an arrow from B to 1. And then we're going to look at our last element in R, C0. So an arrow from C to 0. So we should have 4 arrows between sets A and B, as there are 4 elements in R. Okay, so now we're going to look at relation S. So that relates set B to set C. And we just have 3 elements in S. So let's draw those arrows. The first element in S is 0A. So I'm going to draw an arrow from 0 to A. And then the next element is 1B. So we're going to start in set B at 1 and draw an arrow to B in set C. And then we have 1D. So we're going to draw an arrow from 1 in set B to element D in set C. Okay. So now we've drawn both of our relations R and S. And I want to know, what is the composition RS? So if you were to imagine, you start in set A at some element, like for the first element, little a, and you were to trace these arrows, where would you end up? So that's going to be our relation RS. So let's start at little a in set A and follow these arrows. We're going to start at little a, and we can go to 0 in set B, and then at 0 in set B, that corresponds to little a in set C. So AA is an element in RS. Now, there was a different way we could have gone. We could have gone from little a in set A to 1 in set B, and then could have gone to little b in set C. So we could have gone A to B. And then you see we had another option for A. So we are at little a in set A. We can go to 1 in set B, and then go to element D in set C. So that's AD. Okay. So that was all our options from starting at little a in set A and ending up in set C. Now let's go to the second element in set A, B. So B, we have 1 arrow from B to the element little b to an element in set B. So B goes to 1 in set B. And in set B, we can follow the arrow to little b in set C. So we have BB as another element in RS. Or we could have started at B in set A, gone to 1 in set B, and then actually gone to little d in set C. So that's BD would be our 5th element in RS. And that's all our options for if we start at B. Now let's start at C. And so we have our little a, little c in set A goes only to 0 in set B And from 0, it can only go to little a in set C. So we have CA as our last ordered pair in RS. Okay? And with that, that is our first example of doing a composition of relations. Well, why don't we do another one? But this time, instead of having two distinct relations, then we're taking the composition of those. Why don't we just have one relation? And that relation, we're going to compose it with itself. So let's move on to our example 2. So this was example 1. All right. And if you need to pause the video and finish writing all this down, please do so. We're going to move right on to example 2. All right, so let's consider some set A that contains the elements 1, 2, 3, 4. And our relation R on A is going to be the set containing ordered pairs 1, 1, 2, 1, 3, 2, and 4, 3. All right. And so if we want to compose R with itself, we could draw a little picture first to see what we're actually doing. We have one set A, and R is on set A, so R takes elements from A to A. So let's draw that picture. So I'm going to have, again, 3 rectangles, except this time they're all representing set A. A, A, A. And we're going to compose R with itself. So we're going to go from set A to A using R, and then from there, go from set A to A again using R. So let's list those elements in A. So we have 1, 2, 3, 4. In each rectangle, 1, 2, 3, 4. Last rectangle, 1, 2, 3, 4. And let's draw those arrows for R. So I'm going to go left to right. And R says the first element is the order pair 1, 1. So go from 1 to 1. An arrow from 1 to 1. The second ordered pair is 2, 1. So I'm going to start in element 2, and that's going to point to element 1. And then we have 3, 2. So I'm going to start with element 3, and that's going to point to 2. And then I have the element 4, 3 in set R. So that's going to point from 4 to 3. Okay, seems simple enough here. So now we're going to do this again. So we're going to look at the middle set A, and where all the arrows are all the places we can start. So if you notice, there's no arrow pointing to element 4. So if we have some element in R that starts with 4, that's not applicable here because we can only start at places where we ended. Okay? In the last relation, we only ended at places 1, 2, and 3. We didn't end up at 4. So we can't go anywhere from 4. So let's go from middle column A to the right column A, and mapping points 1, 2, 3 to their appropriate endpoints in the last column here, last rectangle. So using relation R, so R says if you're at 1, map 1 to 1. So we're going to draw an arrow 1 to 1. And relation R says if you're at 2, map to element 1. So we're going to draw an arrow 2 to 1. The third element in relation R says if you're at element 3, map to 2. So we're at 3, and we're going to draw an arrow to 2. And we have another element in R, the ordered pair 4, 3. It says if you are at 4, map to 3. Well, we are not at 4 because there is no arrow pointing to 4 in our second column. So this last element becomes irrelevant. Okay? So we're going to now compose R with itself. So that's going to look like R, R. That's how we would denote that. And to simplify that, we can just call it R squared. And if you know how relations can be set up as matrices, which we did in the last class, and you know some multiplication with matrices, this might even have more relevance to you. But we won't be going over matrix multiplication in this class. But if you know about matrix multiplication, you might see the significance in making this R squared. So let's find all the elements in R composed with R. So we're going to start at element 1 in set A, and we're going to follow the arrows to the rightmost set A. So from 1 we can go to 1 in the middle column and then end up at 1 in the right column. So 1, 1 is an element in R composed with R. And that's all our options for 1. So let's look at starting at 2 in the leftmost column. That points to 2, to 1. Oh, that points to 1 in the middle column, which then points to 1 in the last column. So we should have 2, 1 as an element in R composed with R. And that's all we can do with 2. Then we'll go to element 3 in the leftmost column. That points to element 2 in the middle column, which then points to element 1 again in the third column. So 3, 1 is an element in R composed with R. Then we'll take the last element in A, 4, from the left column. It points to 3. And then 3 points to 2. So 4 to 2. So 4, 2 is an element in R composed with R. So for my final answer, if the question was enumerate or find, something like that, R squared, meaning R composed with R, your answer would be R squared equals the set containing 1, 1, 2, 1, 3, 1, 4, 2. Now, let's do something even more fun, all right? And we're going to maybe use the definition more closely this time, if we were to compose r squared with r, okay? So I'm going to move this paper up a little bit, and let's compose r squared with r. So r was 1, 1, 2, 1, 3, 2, and 4, 3. So let's take these two sets r and r squared, and we're going to compose them with each other. All right. So our definition, again, for doing this composition is if we have some element AB in r squared and some element BC in r, then AC is in r squared composed with r. And in fact, in our definition, it wasn't just an implication one way, it was both ways. So if we wanted to be thorough, we could say AB exists in r squared and BC exists in r if and only if AC exists in r squared composed with r. Now, there's another way to simplify r squared r, and I bet you can guess what that is. So r squared composed with r, another way of saying that is just r cubed. So directions in a question on a test could be something like find r cubed, which means find the elements in the composition of r squared with r. So let's do this. All right, so we're looking for all elements A, B that in our r squared and BC that are in r. That tells us that AC is going to be in r squared composed with r. All right, so we'll take this step by step, and once you get comfortable, it's really not really confusing. You just gotta make sure you're meticulous when you do this. Okay, so I'm looking for some sort of bridge between r squared and r. So I'm looking for, in each of these ordered pairs, I'm looking for the second element in an ordered pair that is the same as the first element in the ordered pair in set R. So if I look at, so I'm going to start with r squared. So if I look at 1, 1, 1 is the second element in the ordered pair. And I'm going to look for a ordered pair in set R that is also 1. And 1, 1 is that ordered pair in set R. So you can think of it like this. 1 goes to 1 in r squared, and 1 goes to 1 in r. Therefore, 1, 1 is an element in r cubed. Okay? Now, we'll go to the second element on r squared, 2, 1. So 1 again is our second element in this ordered pair. So I'm looking for an element, an ordered pair in R such that the first element is a 1. And again, that brings us back to 1, 1. So 2 goes to 1 in R squared. 1 goes to 1 in R. Therefore, 2 goes to 1 in r cubed. And then sometimes you can have more than one connection between two sets. In this case, we had 2 to the 1 in r squared, 1 to 1 in r, and no other coordinate pair in r had a 1 in the first position. So we're done with this. We're done with this second element in r squared. We'll move on to 1, 3 in r. So 3 goes to 1. I'm looking for a coordinate pair that starts with 1 in set r. Oh, again, it's our 1, 1. And that's the only one that starts with a 1. So 3 goes to 1, 1 goes to 1. So 3, 1 is an element in r cubed. All right, we're at our final element in r squared. It's 4, 2. And so I'm looking for an ordered pair in R that starts with a 2, whose the first position is a 2. So the only element in R whose first position is a 2 is 2, 1. So 4 goes to 2, 2 goes to 1, 4, 1 is an element in R cubed. So we have found all the elements in R cubed. And what's interesting about this is that the last, or I should say the second position in each of these ordered pairs is a 1. They're all the same. So my challenge for you is to find r to the 4th, r to the 5th, and in fact, r to the n for all n such that n is greater to or equal to 3. Now this seems like I'm asking you to do something that would take infinite time to do. But you can do this in finite time, and you could do this even with a proof. So this is my challenge for you. Thank you so much for watching. I'm looking forward to next week. Enjoy your spring break. Cheers.